MicroBlocks is a live graphical programming language. It was inspired by Scratch and Snap, and it runs right inside of several microcontrollers, such as the Microbit, the Node MCU, and many other boards, such as Arduinos, M5 stacks, etc. And we've designed and developed the language around 4 basic concepts that we consider to be essential to an educational programming language, so much so that we're calling them the 4 pillars of MicroBlocks. So let me actually show you what these are all about. You should now be seeing the MicroBlocks graphic interface. So the first of these pillars is that MicroBlocks is a live programming language. Being live means that I can click on a block and see the result of the execution immediately. So I don't have to wait for any upload cycles or any compilation or anything of that sort. It is in fact so live that I can modify a program while it's running. So let me build this simple program here, and I can change its speed in real time. Let me actually add in a variable so that I can change both values at the same time. So I'll initialize it to 250. I'll drop the values here. I'll actually put it here as well. So now I could change the interval from somewhere else, make it slower, or make it faster. So this brings me to the second of the 4 pillars, which is that it's a parallel programming language, meaning that I can run several tasks at the same time, as you saw right now when I was clicking on this block in parallel to the script running. So I could have button A make the animation go faster, and button B make it go slower. What else? So this brings me to the third of the pillars of MicroBlocks, which is that MicroBlocks is also an autonomous language. So you maybe have seen this in places like Snap for Arduino or the Scratch extension for Arduino or for the Microbit. But what's novel about MicroBlocks is that you can just unplug the board at any point, connect it to a power source, and your program keeps running in it without any modification, without having needed to press any compile or transpile button or any upload, waiting for any upload cycle. So it's automatically autonomous. Another novel thing of MicroBlocks is that we don't marry one single microcontroller. We are portable by design. So if I plug in this other microcontroller, I should be able to run the exact same program in it, as you can see. And we've taken portability to such an extreme that if you had this board laying around in your drawer, but you had forgotten to save the code, you would be able to select Open from Board here, plug in the board again, and MicroBlocks will read the code out of the board and load it back into your interface. And the program keeps running exactly as it was before. So that was my very short introduction to what MicroBlocks is about. Now I think Barb is going to start some polls that we'd like you to answer while we're doing the session. And I think it's John's turn to show us some stuff with music and MicroBlocks and the Microbit V2.
Okay, great. So I'm hopefully sharing my screen at this point. You see that, Bernat?
Yep.
Great. So when I first heard that the Microbit V2 had both a built-in speaker and a built-in microphone, I got super excited because playing with sound is one of my favorite things to do with microcontrollers. And so practically the first program that I wrote when I first got MicroBlocks running on the Microbit V2 was this program to record and play back sound. And actually, I was really amazed that this actually works so well. So I'm going to just demo this. I'm going to press the A button and say, MicroBlocks is fun. And that recorded about 1.5 seconds or so of sound. And I'll press the B button to play it back, but you probably can't hear that. I'm going to move my microbit over next to the speaker, sorry, the microphone of my computer. Let's try that again. I'm hoping you can hear that. Can you hear that, Bernat?
Yep, we can.
Okay, but it's a little hard to hear, so what I'm going to do is I'm going to connect up an external speaker. So I'm going to connect up, I have one already sort of rigged up, I just have to connect these alligator clips to make it a little bit louder. You can get inexpensive, this is an amplified speaker, so you can get inexpensive amplified speakers. This one costs $5 from Spark Fun Electronics in the US, and I think you can find similar ones online elsewhere. This is called a hamburger speaker, just so you know. Looks kind of like a hamburger. I have to make one change to the program. Instead of outputting to pin 27, I'm going to output to pin 0. And with that change,
MicroBlocks is fun.
Hopefully, it's now coming at you loud and clear. So, having done that, oh, actually, before I go on to the next section, I want to point out that this actually shows you all of the steps of digital sound processing. So we started with my voice, which created sound, basically little tiny fluctuations of pressure. Those moved a diaphragm in this tiny microphone in the back of the microbit, creating a changing voltage, which was converted to numbers by the analog to digital converter in the microbit. And then those numbers were stored in this long array of values, 20,000 values. To reverse that process, what we did was we stepped through that array and we set the pin to that number, and that created a changing electrical signal, which drove the speaker, which made sound waves, which came to my ears and through the internet to your ears. So we totally reversed the process. I want to also show you the what that looks like if I graph it. So this block right here steps through those same samples and displays them on this graph. So you can see here, this is the actual instantaneous sound pressure levels that were recorded, one every like roughly 15,000th of a second apart. So if you can record sound that quickly, then you can actually reproduce it in a way that we can understand. Okay, if you can do all of that, I thought, well, you should be able to do something that I've also wanted to do with microbits ever since they came out, but didn't succeed before, and that is to play multi-part music through a single speaker or harmony. So I'm going to open up another project that demonstrates that. This is, I'm going to move this out of the way so you can see this better. This is a round, so it has 3 parts. This is the notes for part 1, the notes for part 2, and the notes for part 3. Some of you will probably recognize the tune. And I'm going to start off by playing each part just in sequence. Part 1, wait until that finishes. Part 2, wait until that finishes. Part 3. So let's hear how that sounds.
John, I think you should.
So that's something we could already do with the microbit version 1. But now what I'm going to do is I'm going to play it like a round. So part 1 will start. Then part 2 will join, actually singing part 1 as the first part sort of goes on to its part 2. And then we'll have a third voice join, and we'll have all 3 parts, and then the voices will start dropping out. So here we go as a round. 2 parts. All 3 parts. 2 parts. 1 part. And then a final last note. So the way this works is that it actually synthesizes 3 waveforms. It actually can go up to 4, and it adds them together, and then it outputs the result of that addition as the sound sample, and it does that roughly 15,000 times a second. Well, so there's another. Oops, I didn't mean to open that. There's another synthesis technique that we can use. Which is to synthesize a string pluck, like a guitar string. And I'm going to start by just playing that so you hear what it sounds like. So this synthesis technique is, it's called the Karplus-Strong Plucked string algorithm, which is a big mouthful. But it turns out it's a very simple algorithm, easy to implement and pretty efficient, so it can run on a microcontroller. And the way it works, I'll actually play a short version or a high-pitched one. Whoops. I don't know if you heard that. That's a little teeny pluck sound. So the way it works is it starts with a buffer of a certain length. This is a buffer of length 20. It fills that with random numbers, and then it outputs those as the sound output, and it sort of steps through the buffer. And every time it outputs a sample, it averages it with the one next to it. So the result of that is that it gradually sort of smooths out the random numbers so that they kind of start forming an undulating thing. The period of the sound is determined by the length of the buffer. So if I make this twice as long, we get a lower note, and if I make it twice as long again, a lower note. And let me go to sort of a couple of steps, 320. And if you want a really low note, like the lowest note on a piano. So it's sort of amazing how simple, or how this simple algorithm generates something that feels like a very organic, natural sound. The cool thing about MicroBlocks is that we have this Plucked library that has a kind of a simple API, play a note or play a MIDI key, but I can look inside of it. This is the kind of core of the algorithm, and I can show the definition for that block. And you'll see that this whole library was written in MicroBlocks itself. So this algorithm, which is all just right here, is written in MicroBlocks, and you can actually follow it and understand it. Here's the part where it averages two adjacent samples. To understand it better, I'm going to add this graphing thing, and so we can actually take a look at this as it's generating sound. But I'm going to go back to a short buffer size because that's going to be easier to kind of see as it evolves. So let's see what happens. So one thing you'll notice is that the sound is being interrupted by the fact that it's graphing. But you'll also notice, I just hit it again, you'll also notice that as it plays, it's getting more smooth. So it started out chaotic. Let's do one more. Chaotic. And then as time goes by, it gets rounder and rounder, or smoother and smoother. It also diminishes in amplitude, so that the distance between the peak-to-peak distance in this waveform gets lower and lower, and that makes it sort of fade away in time. And that all of those things together gives you this kind of effect of a string that's been plucked. So with that, I'm going to stop sharing and turn it over to Bernat, who's going to show you some other fun things that we can do with sound and music.
Okay, so I just wanted to show you how, as John was saying, all these blocks are built in MicroBlocks itself. So actually, even the play note block is written in MicroBlocks, as you can see here. And this is how you used to make music in MicroBlocks. So you would use the, I will stop this now. You would use the play note block, and you would use repetitions and weights and so on. And you would maybe use variables to define the duration of the note so that you could change the speed at which you play the melody. But that was about it. It's a kind of verbose way and very cumbersome way of writing music. So the other day, while playing with music, I decided to implement this, to invent this format, this text format for representing music. And it's pretty much the same thing, right? You define in three, in groups of 3 elements, what the note is, what the octave is, and what the duration is. And while I was showing this to Kathy and John, I remembered that as a kid, I used to have a Nokia phone, not a smartphone, an old phone, and you would write songs in it in a textual form with something called the Nokia ringtone transfer text language, something like that. So I looked it up and I decided to implement a parser and player of this format in MicroBlocks. So you can see that we've gone from a very long program to a very short and expressive one. And let me show you that this is actually all written in MicroBlocks. And actually, while we're at it, John just showed us that you can simulate a Plucked sound in MicroBlocks, so we should be able to modify the code that I wrote to play a single ringtone note. And instead of playing the note using our built-in play note block, we could just substitute that with the new Plucked note block that John made. And let's see what happens.
Can you hold it a little closer to the microphone and do that again?
Oh, yeah, sorry.
Oh, much better. That's hilarious.
So it's some sort of like a violin pizzicato, right? The nice thing about this is that every single part of this, including the libraries and the most low-level things that are pretty much all written in MicroBlocks, and you can explore them and modify them.
Cool. Okay, so I'm going to talk now a little bit about using the microphone as a sensor, not as a sound recording device. And I'm going to start by running this script here, which turns the microphone on, and then it graphs the loudness. And Bernat, am I still alive?
Yep.
Good. Okay. So here we go. I'm going to graph the loudness, and I'm going to change this graph to put 0 at the bottom to make it a little bigger. But you notice as I talk, the loudness goes up and down. Loudness is a little bit different than just reading the raw microphone volume. In order to sort of get an approximation of loudness, it actually senses a little chunk of sound, like maybe 10 milliseconds long, and it figures out what are the maximum and minimum in that period of time, and figures out from that the sort of peak-to-peak value of the sound, which is an approximation of its volume. So you can see as I talk, it makes spikes, and if I am silent, it goes down to a value near 0, around 20 or so. If I clap, I can make a bigger spike. So I'm going to use the fact that the clapping is a lot louder than my normal voice range. Like my normal voice range goes up to 200 or 250, but claps go off the top of the chart there. So I'm going to use that fact along with this script right here to count the number of times I clap. So there's a clap count also written in MicroBlocks, which waits to see how many times I clap and then reports that as a number. And this threshold here says it has to be above that volume, so above 300 for it to count as a clap. So let's see what happens. Okay, 1 clap. 2 claps. 3 claps. So now that I can record claps, I'm actually going to use that number to drive these scripts over here. So I'm going to broadcast the number of claps as a message, and these scripts are going to receive the message, and it's going to either trigger 1, 2, or 3. So let me just drop that in here, and I'll try 1 clap first. So you'll notice, first of all, that it triggered this animation when I clapped once. But you'll also notice that there's a little delay between the clap and the animation. And that delay is, well, it's waiting to see, am I going to clap again? Oh, it just picked up my voice as if it were 2 claps. So this threshold is maybe a little bit too low. So it has to wait to see, are you going to clap again? And should I count that? Or are you done clapping? And that delay is about a second. So that gives you the delay before it responds. So let's try a couple of other patterns. 2. Oh, 2 was already what it's showing, the snowflake. 3. 3. Back to 2. All right, so that's pretty much the end of our demos, though I wanted to just say that as I was working on all these sound examples, I was using MicroBlocks as a tool. So I was using the graph tool especially to sort of see what was happening and to debug my synthesis algorithms and everything and understand what was happening. So I was really using MicroBlocks as a serious development tool to explore something I hadn't explored before. And I think the live nature of it that Bernat was talking about really makes that process productive and also very fun and rewarding. And I think that even though I was doing something maybe more complicated than what 5th graders would do, the same feeling of sort of liveness and instant responsiveness applies to them. They are also captivated by the ability to change stuff on the fly. Okay, so with that, we'll turn it over for questions.
Thanks, John. I'm going to pop your last 2 questions, the last 2 polls, and make them live.
And see, if people have questions, I haven't been monitoring the chat because I've been too busy talking.
Some people have
Bernat has been awesomely answering.
Oh, great.
So somebody asked about whether we have materials for children to show all this stuff and teach all this stuff. I replied that we do have activity cards in our website. We don't yet have.
I'll show that, Bernat.
Yes,
share my screen. So here's the MicroBlocks website. You can download MicroBlocks here, but also in this Learn section, we have some like very simple things like this Getting Started activity guide. These are really designed for teachers and students to use. So they're in the classroom. So they try to really simplify the steps. This one is like an early activity for just like making the buttons control stuff. And we've used this. I've walked into a class, a group of like 6th graders, given them a 5-minute introduction to MicroBlocks and handed out these activity cards. And within 45 minutes, they were doing amazing things. And I only had to talk for 5 minutes. So the cool thing about these activity cards is they take a lot of the burden off of the teacher to explain stuff because the students can learn on their own.
We didn't mention that we've just recently entered beta, so we're really looking forward to people using it and giving us feedback. The software has been in development for 3 years, and we think it's pretty stable. It's been used a lot by some of our early adopters. We've only just called it beta now because we were missing one feature, and now we have it. But yeah, we're looking forward to your feedback.